Okay, this is a packet tracer video using redundant links on server farm devices. So we have two topologies here. The first one here and then our second one there. In our first topology, the physical topology of the first topology has been designed without redundancy. So to test the fault tolerance of the network, we're going to remove some of the links to test the effects on the network and to determine if the network can recover from a removed link. And then in topology 2, it's been designed with redundancy. So we are going to remove one of its links and test the fault tolerance of the network after the link has been removed to determine if it can recover from the down link. So the first thing we're going to do is look at the topology number 1. And right now we have connections on everything. All of our servers go to the server A, and it goes to the router, to the access A, which goes out to our workstations. And all of them have active links. So there are no blocked ones. So we're going to open up PCA and go to the command prompt, and we're going to ping 100 ICMP request to server A. So we're going to do a ping -n 100 because we want 100 requests, space, and then the IP address 192.168.2.3. And that will go 100 times, and at the end we'll get a result. So most of these are going anywhere from 0 to 1 millisecond. That's how quick it is. I haven't seen one over a millisecond yet. Okay, so ping statistics for 192.168.2.3 is packet sent was 100, received 99, lost 1, which is 1% loss. Approximate round trip time in milliseconds was a minimum was 0 milliseconds, maximum was 10 milliseconds, average equals 0 milliseconds. Okay, so now we're going to delete the link that goes from router A to server A. So we're going to take this link out. Right here. And we're going to view the network and note that the active links, which they're all still active, but there is no network redundancy because we took one of our main links out. So if this link goes down, we're not getting anything here. The PCs can't talk to the servers, and the servers can't respond back. So therefore, a single point of failure within the network pretty much shuts this network down, and there's no longer a route to the servers. So then we're going to go down here to topology 2, and we're going to examine topology 2. We have all active links. All the green ones are active. This is blocked. This one's blocked. This one's blocked, and this one is blocked. These are your redundant links. So if a link goes down, one of these is going to come on. So we're going to open PC1B, and we're going to go to the command prompt, and we're going to type in ping we're going to ping the server web A dash n 100 times ICMP requests. Which we already did 100, 192.168.4.6. And then while that one's going, we're also going to start one over here on PC2B, and it'll just run back there in the background. We're going to do another ping 100 192. We're going to ping the server marketing B 168.4.6. So we have both of them going on at the same time. This is the PC1B. It should finish first. There's one there that was 12 milliseconds right here. Okay, so on the PC1B, when we pinged the server web, we had sent 100 packets. We received 99. We lost one, so we have 1% loss. And it took it an average of 0 milliseconds, and it was a maximum of 12 milliseconds. And on PC2B, where we pinged the server marketing B, we had sent 100 packets, we received 100 packets, so we had 0% loss. And it took, the maximum was 14 milliseconds, and the average is 0 milliseconds. So now we're going to delete a link between server 1B and the switch 2B. So we're going to delete the link between server 1B right here and server 2B. 1B, 2B. So we're going to delete this dude. And watch our lights. So right now we have 1, 2, 3, 4 blocked. And one of those should pick up now that we've taken this link out. One of these should kick in. Now these two lights went blank. Or they're blocked now. So something's going to... See, this one turned green. So we have a connection going this way now. And we can go this way now. So you can go this way to get it here, this way to get to these, and we can go this way now to get over to here, because these are all green. So we only have 3 blocked ports. So our redundancy worked here. Okay, so okay, the spanning tree should recalculate and automatically begin using the alternate links, and that's what it did. So delete the link between switch 3B and server 3B and switch server 5B. 3B and 5B, so it's going to be right here. Okay, so we have 1, 2, 3 blocked. You can go this way here, but you can't come down this way. You can't go that way. So right now you can't do anything here. This is blocked here now. Okay, so now we can go here. So we took this link out, and you can go up from server 3 to server 4 and down to server 5. And you can go from server 3 up to server 2. Now, why you cannot go from server 2 over to server 4 is beyond me. Why that's not. Because we only have 2 block links now, and it's this one and this one. But we still have ways of getting around. You can go from server 2 to server 3, up to server 4, down to server 5. So it still all works. So if you're using equipment without redundant, using a network without redundant equipment, and something goes down, you're pretty much dead in the water. So if we were to add an additional switch to our topology 1, if we were to put another switch in here and add redundant extra links in here, we would, and it went down, we'd have a way to get around it. Right now, this you can't. So a network that's designed to have redundancy and spanning tree is disabled on layer 2 switches, what effect would that have on your network? If your spanning tree is disabled, it prevents the load balancing over the redundant links. And plus it will kick in when it needs to be. When you need to use that link, it'll kick in. Alright, so that concludes this video. There we go. And I thank you very much for watching it and putting up with me. And I hope you have a super blessed day. Thank you.